Naidu coming to you from the Minecraft world, and today I'm going to be looking at some revision of the chemistry we've been doing in booklets 1 to 3, and then be looking at a past paper to help you with some exam answering strategies ahead of your test tomorrow. Right, so the first thing you should do when studying after you've gone through your notes is trying to identify what are the key things that each book was about. So you can get most of this from the title, but book 1 was about matter and the periodic table. And the key things underneath matter was about how do we classify matter as being an element, a compound, or a mixture of one or the other. And the way this was shown is by having elements represented as circles of one color, compounds represented as having different colors, and mixtures just having them loosely put together in any combination. So this particle model is very important because it's an easy way to represent how and why we classify matter, where each circle represents an atom, each group a molecule. And if you've tried that paperclip activity, that's a very nice way to understand those 4 keywords: element, compound, atom, one circle, and a molecule, a group. It's the scientific terminology that we use. The periodic table, on the other hand, can be summarized in literally 2 pages. That first page, which has the names and symbols of the elements, that is simply a matter of learning. And then that single colored in page, which had key at the bottom, nicely colored in. It had your phases that you need to know. It had the magnetic elements and the diatomics. So if that periodic table is completely colored in, if you look at that, study it, test yourself, then you will know what it is you need for the periodic table. Let me just say, it's not only what I'm looking at today that's in the test. You must, as was instructed on Teams, have a look at book 1, book 2, and the first few pages of book 3. Book 2, on the other hand, was all about naming chemical formulae, writing those chemical formulae, and then writing them in equations. And we spent the bigger part on book 2 in how do we balance those equations. So before I look at a past paper, I'm just going to look at 2 simple examples, maybe 3, about naming formulae and balancing equations. So when it comes to naming compounds, this is where you're given a bunch of symbols, and we have to be able to name them based on just the symbols. So the first thing to identify is, are we dealing with a metal and a non-metal, or 2 non-metals? We will never have a metal bonded to a metal and call it a compound. So if I had to name something like NaN, first thing you must recognize is that sodium is a metal. And whenever we have a metal, it's a lot simpler in that we just write down the name of the first element, and the second element, which has to be a non-metal, changes into an iode. And you need to know how it changes into an iode. It doesn't just become nitrogen and then iode. Nitrogen changes to an iode. So that is when you're dealing with a metal and a non-metal. First thing to look for. BeCl2, that again has a metal. It also has a very tricky spelling. BeRyLLium. Chlorine changes to chloride. That's as simple as it is to name metals and non-metals. When you have 2 non-metals, it's not that much more difficult. The only thing you need to remember is where we use these prefixes. So hydrogen is a non-metal. Very quickly, how I know that is on your periodic table. Hydrogen is on the left-hand side of, hydrogen is above the steps, so it is a non-metal. The other non-metals are all on the right. Metals are on the left-hand side of the steps. Okay, so if I have 2 non-metals, we name this by putting a prefix in front wherever we have more than one of an element. So this becomes dihydrogen, put a space because it's 2 words, and sulfur changes into sulfide. H2O2. So there are 2 ways to name this. In the notes, it was given as a name of hydrogen peroxide, which is a correct name. But naming it according to these di and tri rules is something we call the IUPAC name. And that name would be given as dihydrogen because there's 2 hydrogens, 2 oxygens, becomes dioxide. And that's as simple as it is to name metals and nonmetals. Next, going from a name to a formula. It's not that much more difficult, but the key thing that you need to know in order to do this is to have some idea of valency. And valency are those little numbers on the periodic table that go +1, +2, +3, ±4, -3, -2, -1, and 0, depending on which group we are in on the periodic table. The pluses and minuses are not so important, and if we had something like, say, hydrogen and chlorine, both of their valencies we can say are the same, even though it's a plus and a minus. So if I had to take a compound like, let's go with potassium oxide, and I had to write a formula for it, first thing is to take the symbols of the elements, K and O. So if you don't know those symbols, you can't do very much. The second thing is to look at their valencies. Potassium has a valency of 1. It's in group 1. Oxygen has a valency of 2. The minus doesn't really matter. And the shortest way to determine these formulae is to just remember this, what I call the swap and simplify method. In this case, we're just going to swap the valencies. This one goes here, this 2 goes here, and my formula is just K2O. The 1 does not need to be written, but you can if you want to. Let's take it one step further. If I had, let's go with silicon oxide, symbols are Si and O. My valencies are 4 and 2. So this time when you swap the valencies and put the 4 here and the 2 there, you must remember to simplify the ratio between those valencies. And this will simplify into SiO2 because both the 2 and the 4 have a common factor of 2. So my correct formula is SiO2. All right, and then lastly, as if we had a terrifying name like diphosphorus pentoxide, where it has these prefixes, you don't need to consider the valencies at all. The di tells me there's going to be 2 of the phosphorus, it's P2. Pent is the prefix for 5, so there are 5 oxygens. And that is the naming done for 2 nonmetals. Okay, then I want to look at maybe just one example of an equation which represents an equation or a chemical reaction in words using the names of the symbols and compounds. We can also represent a reaction as a chemical equation. A chemical equation is where we use symbols. And lastly, we can also represent it using particle diagrams, or this is sometimes known as a picture equation. And it's very important you're familiar with these terms so that you know what it is to do. So if I take a very simple reaction, let's take sodium and react it with oxygen. Notice I say react with, but we write it as a plus. Reacts to form. Now, even though we call it an equation, there is no equal sign that appears anywhere. That arrow shows that we use energy, and that makes them explode to form sodium oxide. And I got this name from our chemical naming, that the second word changes into an ide. Now, to write this as a chemical equation, there are 2 questions you need to ask. Firstly, what is the symbol of the element? It's Na. And secondly, is it diatomic? If it's not diatomic, it just stays as the symbol because it is therefore monatomic. Oxygen is diatomic, and that is the only time we change the subscript of an element by itself. Now, diatomic only refers to elements. When oxygen is in a compound, the word diatomic no longer applies. And this is a place that you need to be careful, is even though we have Na reacting with O2, to find the formula here, we don't simply push them together and say NaO2. In the same way, you wouldn't tell me that 1 + 1 is 11. You have to work it out. And we work this out using that swap and simplify method, using the valencies. So the valency of sodium is 1. That would swap and go by the O. The valency of oxygen is 2. that swaps and comes here. And my formula is Na2O. So in a chemical equation, always work out the right-hand side separately. And it might not look natural as to how Na becomes Na2, but that is why we balance the equation using big numbers, which I'm going to do here very quickly. So to write it as a balanced chemical equation, I'm counting the number of atoms of each element. There's 1 on the left, there's 2 on the right. If I had to put a big number 2 here for now, that means I have 2 sodiums, which is balanced. If I check the oxygens, there's 2 on the left, 1 on the right. I'm short on this side, and that's the side I'm going to put a big number in front of. Big numbers. You can never balance an equation by changing small numbers. So if I put a 2 here, that does indeed multiply and give me 2 oxygens, but it also changes my sodiums, because now I'm going to have 4 sodiums on the right-hand side. On the left, I had 2, so I'm going to change the big number into a 4. So my balanced equation will read 4Na plus O2. You can put a 1 in front, it's not compulsory, but it helps me know that I have checked that the oxygens are balanced. Gives me 2 Na2O. All right, so then lastly, to draw this using particle diagrams, that's using little circles. Those circles will mean absolutely nothing unless you tell me what it is they're representing. And this is in the form of a key. And the key is simply using simple symbols to tell me which element is represented by which symbol. Right, so in drawing this equation, we're going to start with the unbalanced equation. Na is just 1 atom. Oxygen is diatomic. That is why there are 2 atoms and touching. That's important because they're bonded. And that gives me Na2O. So Na, I need 2 of them. That's 2 circles. Oxygen, 1 shaded circle. And this is the compound Na2O. Now to draw the balanced particle diagrams, I need 4 NAs, but they will be 4 separate circles. They are not chemically bonded. Sodium is monoatomic. I have my 1 oxygen molecule, and to show 2 sodium oxide groups, I'm going to the next line and drawing it separated. So then I can easily count. That is why there's a big number 2 in front of the Na2O, because I've drawn the same compound 2 times. There's only 1 group of that. That is why there's a big number in front. But because there are 2 atoms in that molecule, that is why there's a small number. And lastly here, there are 4 different, well not different, 4 of the same atoms. That is why there's a big number 4 in front. At a past paper and some general tips for answering exam questions. Right, so firstly, under Teams, if you forgot or never knew, in the Files tab in the General channel, Grade 9 Science, there is a Tutorials and Past Paper folder that has got a number of past papers and memos from the last 3 years that you should be using to familiarize yourself with how questions are asked and to practice, most importantly, because that is the most important thing in studying physical science. It's all about the practice of questions. Right, so the paper I'm going to be looking at is a winter assessment from July 2020. So even though this is a mid-year exam, we won't be able to answer all of the questions, but there are a good number of questions that do cover content on the chemistry we have done. So firstly, in an exam, it's worth taking a minute or 2 just to read over the instructions. Now, something you take for granted is to check that your paper is complete. Don't want to answer half an exam. And what's also important about these exams that we will be writing is that they are all full-on exams. So there are spaces for you to be answering the questions. Right, a paper will always start with multiple choice, about 10% multiple choice questions, each one out of 2 marks. And I would perhaps suggest do them at the end of the paper because sometimes they take a bit of time to get through, especially a complicated question like this. And 2 marks should indicate to you should be spending 2 minutes. But if you do the multiple choice first, you might end up taking a bit more than that. But I'm going to start from question 1.6. The rest of the questions are in physics because it looks familiar, and this is on chemistry. So the question says, which diagram below correctly represents a mixture of two compounds? So there are two technical science words here that we need to be familiar with, a mixture and a compound. So a mixture, by its definition, is where you have a substance made of different elements or compounds not chemically bonded. So to show two things are not chemically bonded on a picture, there'd be a gap between them. A compound, on the other hand, is where we have different atoms or different elements that are chemically bonded. So if I look at picture B, this white circle is representing an atom, the black circle is an atom of a different element, and because the two are joined together, this would represent a compound. If I look at what else is in the block, there is another compound here, but it has the same ratio of black to white atoms. So in picture B, all of the groupings of atoms, or we say molecules, are exactly the same. So picture B is only showing me one compound, which is not going to be a mixture. I'm looking for a mixture of two compounds. If I have a look at picture A, also looks a bit similar in that we have a compound here, we have a compound here, but if you look at them carefully, you'll see they are different compounds because they have different ratios. This molecule has two white atoms and a black atom, chemically bonded because they're touching. This molecule has two black atoms and one white atoms. So this is showing two different compounds. This and this are exactly the same. This and this are also the same, but the pairs are different to each other. So picture A is going to be my choice because it shows two compounds and they are mixed together, which I can tell from the space between them. So just quickly describe B, C, and D for the purpose of revision. So picture B, we said, is showing me one pure compound. Picture C is just showing me one element. An element is where you have one type of atom, not bonded to anything different. Picture D is showing me, well, it's a mixture because we have different groups, and it's a mixture of one compound, those two are the same, and one element. Okay, question 1.7. Which of the following equations is correctly balanced? So I'm looking for two things here. I'm first looking to see that the equation is correct, and then secondly, I'm looking to see that it is balanced. Now, for an equation to be balanced, it means the number of elements I have on the left-hand side must be equal to the number of that same element on the right-hand side. So let's have a look at A. So in A, I have Al2, counting the aluminiums to start with, and on the right, I also have Al2. So the aluminiums appear balanced. If I look at the hydrogens, there are two on the left, two on the right. Hydrogens are balanced. If I look at the sulfurs, there's one there and one there. That's also balanced. And then oxygen, 4 and 4. So sulfur is balanced, oxygen is balanced. So it appears to be that A is correctly balanced, but it is not correctly balanced because there is a small 2 over here, which aluminium should not have. Might be something that you noticed immediately that was wrong with A. Aluminium is a metal. It is not diatomic, so it should not have a small 2 next to it. Very subtle thing about how the equation is balanced, but the equation is not correct. Aluminium is not diatomic. So A falls out of the mix. If I look at option B, so perhaps this time I'll first see if the equation is correctly balanced. So Al has no small number because it's not diatomic. H2SO4, that is correct because sulfate SO4 has a valency of 2-. Hydrogen, the H, has a valency of +1. I've got 2 of them. So if I write it like this, sulfate is a -2, hydrogen is a +1, but I've got 2 of them. So in total, that's +2. The valencies in this compound all add up to 0. So H2SO4 is correct. On the right-hand side, H2 is correct because I know that H is diatomic. And over here, I've got Al2SO43. So to check that the small numbers are correct, we're going to have a look at SO4, 2-, has a valency of -2. That's your sulfate polyatomic ion. Al is in group 3 of the periodic table. It has a valency of +3. And I can multiply the valencies by the small numbers, because the small numbers tell me how many atoms of the element I have. So if I have Al2, that means I have that +3 valency 2 times. If I have SO4 3, means I have the sulfate ion 3 times. And if you add all these valencies together, +3 plus 3 is +6. +6 minus 2 is 4, minus 2 is 2, minus 2 again is 0. That makes this compound neutral. So that formula is correct. Now to check the balancing. So balancing is all about the big numbers. So I'm going to start by counting the aluminiums. So the big number 2 times the imaginary 1 here means I have 2 aluminiums. If I count on the right hand side, well, there I already have 2 aluminiums. So in option B, my aluminiums, there's 2 on the left and 2 on the right. If I count my hydrogens next, got some big maths here. So the big number 3 distributes and multiplies by the small number. 3 times 2 is 6 hydrogens on the left. If I count on the right hand side, I again have 3 times 2, which is 6 hydrogens. If I count the sulfurs, there's 1 in the formula, SO4, but it multiplies by the 3 in front, so I actually have 3 sulfurs on the left. On the right hand side, there's 1 sulfur inside the bracket, but that small number 3 also distributes, meaning I have 3 sulfur atoms as well. And then finally, for the oxygens, 3 times 4 distributes, giving me 12 oxygens on the left. And on the right hand side, 4 distributes by the 3 outside the bracket, giving me 12 oxygens as well. So my answer here is going to be B. There's no need to check C and D, because you can tell how long it took us just to go through A and B, but picture option B is going to be my answer here. Okay, so 2 things to take away from checking if an equation is correctly balanced is to 1, check that the formula is balanced. Sorry, check that the formula is correct. That means checking your diatomics are diatomic and nothing else. Check that the valencies in a compound add up to 0. And then the second thing is when checking the balancing, remember to distribute the big numbers in front when you're counting. And whenever you're dealing with a polyatomic ion, those are often in brackets when there's more than 1. Those numbers also distribute. All right, question 1.8. Which row contains the correct IUPAC names for the following compounds? So an IUPAC name is basically the international name for something, the official name that we have for a compound. Okay, so looking at the formula in the first row, I have H2O2, that is not water. Water we know is H2O. Hydrogen oxide, well, we could call it that, but we know that when you are naming metals, non-metals with non-metals, that is when we use the prefixes di and tri, etc. Option C says hydrogen dioxide, so there is indeed 2 oxygens here, so dioxide would work, but there are 2 hydrogens as well. So if I was naming it dioxide, I wouldn't just name it hydrogen, I would name it dihydrogen dioxide. So this option is correct. But this is a whole table and we need to check through all the options, not just the one option and then go to D. Okay, the second column, methane, well, that is technically a correct name. Carbon hydride, you could call it that because it's carbon and hydrogen. But again, we have 2 nonmetals, and when we have 2 nonmetals, I'd like to use the prefixes, tetra meaning 4. So carbon tetrahydride is correct. Carbon tetrahydride, it's the same thing, is also correct. So D is looking pretty good at the moment, but I need to check with my last column. So I have NH3, it's called ammonia. That is technically a correct name. Nitrogen hydride will also be technically correct. Again, nitrogen and hydrogen are both nonmetals, so I'd be using the tetra and the tri in this case, because there are 3. So this is correct. Then lastly, nitrogen trihydride repeated is correct. So even though it might seem that there are more than one correct answer, in a multiple choice, you're always going to take the most correct answer when naming something. And so my answer here is D. What's important in this question is, if you just glanced at it, is that we are looking for IUPAC names. IUPAC, like I said, international names, are also how we name things systematically, meaning according to a list of rules. Those rules meaning using the di, tri, and tetra, where you have more than one nonmetal. All right, question 1.9. Have the numbers of protons and neutrons been correctly identified for the given elements? So to answer this question, I need to know where I can find the protons and neutrons, and the answer to that is the periodic table, and 2, where that periodic table actually is. So you can find a periodic table in the test on the last page, a data sheet, to look exactly like this. And on the left-hand side of each block are 2 numbers, and it's given to you as a key, where it tells you the atomic number, Z, is the top left number, and the bottom left number is the relative atomic mass, or what we've called as the mass number. So on the question, it has cobalt with 32 protons and 27 neutrons. So if I find where cobalt is in the periodic table, it is CO. So also in this question, you need to know your names and symbols for the elements. Cobalt has an atomic number of 27. I know it's the atomic number because the key tells me it's the top left number. And the atomic number is going to be the number of protons. So cobalt is supposed to have 27 protons. In the options in the multiple choice, it says 32, so A falls away. Calcium, it tells me, has 40 protons. If I find the symbol of calcium, its atomic number is 20, so that falls away. Option C, it says iron has 26 protons. Iron symbol is Fe, that's over here, and its atomic number is 26. So iron has the correct number of protons. It also tells me iron has 30 neutrons. Now, to work out the number of neutrons, we take the mass number, or the relative atomic mass, which is the bottom left, and subtract it from the atomic number. The reason for that is the mass number is telling me how many protons and neutrons together. So if I just minus the protons by themselves, I will get the number of neutrons. So 56 minus 26 is indeed 30. So option C is the correct option. Okay, and lastly, question 1.10. Which of the following elements are non-metals and exist in the liquid phase at room temperature and pressure? So where you can find this, or what you've studied, is that colored in periodic table where we highlighted all the different groups of elements and put a key for their phases, the ones that are gases, the ones that are solids. We didn't put a key for, because anything that is not a gas or a liquid has to be a solid. And finding metals and non-metals, that was indicated by the steps. Everything on the left was a metal. So Hg, again, going to go back to my periodic table. Hg over here is on the left-hand side of the steps, or if you're familiar with mercury, it is a metal and it is a liquid. The second option, Br2, that's bromine over here, is a liquid at room temperature. It's on the right of the steps, which is a non-metal. And 3, H2O, is not on the periodic table because it is a compound, not an element. Okay, so returning to my options, Hg, Br2, and water. So the question is asking me to identify elements that are non-metals in the liquid phase. So I've eliminated mercury because that's a metal. Bromine was a liquid and a non-metal, and I can eliminate water because it's not an element at all. So my option here is B, 2 only. Right, so that was the multiple choice. Next, I'm going to be looking at a long question. This is question 6. Which, as always, starts with a story. Now, these stories here are to test your reading skills and also to see if you can find out what information is important. And the last purpose is it just makes the exam papers a bit more entertaining. We already know that Michelangelo loves pizza. Michelangelo suffers from hypophosphatemia, low levels of phosphorus. So just up to here, you might already be panicking and not even know who Michelangelo is, one of the Ninja Turtles. It's mentioned earlier in the paper. And this funny word, hypophosphatemia. Now, even if you don't know Michelangelo or phosphatemia or love pizza, that is irrelevant to the question. So these first two sentences have nothing to do with what we need for the question. Keep reading. Tripotassium phosphate, K3PO4. And that sounds a bit familiar. We've seen a formula like K3PO4 and phosphate, so I'm going to underline that. Tripotassium phosphate is used to treat or prevent hypophosphatemia. And we can see why. I mean, phosphatemia is low levels of phosphorus, and that has phosphorus in it. So Michelangelo sprinkles tripotassium phosphate powder on every pizza he eats. One day, while Michelangelo is making his own pizza in their kitchen, in their sewer home kitchen, the Teenage Mutant Ninja Turtles get a WhatsApp message. Their help is needed urgently to stop Bebop and Rocksteady, evil members of Evil Shredder's Foot Clan, who are causing trouble in the city. Nice story, but no science I need to take away from there. They leave their home in such a hurry that Michelangelo forgets about his pizza still in the oven. Right, question 6.1. Define compound. Define. Define is a very specific word in science that means you must repeat the definition from the notes exactly as it is, word for word. So definition of a compound, and I have the idea, which is where you have two different elements chemically bonded, as I discussed in that one multiple choice question. The definition you write down exactly as that. A substance formed when two or more different elements are chemically bonded to each other. So this stage, I'm just going to switch over to a piece of paper for writing the answers to these questions, not being multiple choice. So compound definition, this is how you would be answering questions in a test, word for word. A substance formed when two or more different elements, and this is a key part of the sentence, is two or more different elements are chemically bonded. And that is a definition. The question is not asking you to explain in your own words or to describe a compound. It says define. Question 6.2. Classify K3PO4 as either a compound or a mixture. Give a reason for your answer. So more often than not, whenever a question asks you to define something, the next question is implicitly suggesting that you should use your definition to answer the next question. So K3PO4 is going to be a compound, and the reason why has to do with the definition we've just written down. That in K3PO4, those symbols represent different elements. They are all written together with these numbers here in a formula to show that they are chemically bonded. So now all we need to do is we need to explain that. It is a compound because different elements, and what are those different elements? Potassium, K, phosphorus, and oxygen are chemically bonded. How do I know they're chemically bonded? Are written in a chemical formula. And that's a good enough reason. Now this question is out of 2 marks, which means that you need to have at least 2 things in it. Give 1 mark for saying it's a compound and 1 for the correct reason. Always use the mark allocation as a guideline for not only the time you should spend on a question, meaning 2 marks would be about 2 minutes maximum, slightly less than that, and that you should have 2 things in your answer. Question 6.3. How many atoms are present in a molecule of K3PO4? So this is a simple matter of counting and knowing that the small numbers tell you how many atoms of the elements there are in the compound. Next to the P, there is no number. There's always an imaginary 1, just as in maths. X is the same as 1x. So to get the total number of atoms, it's a simple sum. 3 for the K, 1 for the phosphorus, and 4 for the oxygen is 8 atoms in total. Question 6.4. Name the group on the periodic table in which potassium is found. This is just a learning question. If you know where K is on the periodic table, remember you have one on the last page. K is in the first column, which is group 1. But the question didn't ask me to number the group, it said name the group. This is one type of question where you can know your science, but you miss a keyword like name, and you miss out on the mark. The name of group 1 in words is the alkali metals. As easy as the question might seem, make sure that you read what asking. 6.5. Identify each element present in K3PO4 as a metal or non-metal. So the 3 elements here are given by the 3 different symbols. So that is K, P, and O. I'm going to name them. It says identify. And once you identify the symbol, they're already there. It's good practice to name them and identify them as a metal or non-metal. So the metals we know are found on the left of the periodic table. Remember those steps on the line. So potassium is on the left, it is a metal. Phosphorus is on the right, a non-metal. And oxygen on the right as well is a non-metal. Right, moving on to before question 6.5. Burnt beyond recognition. Michelangelo is distraught. Raphael, or his Joker, thinks the burnt pizza is hilarious. Question 6.6. Write the specific word equation for the chemical reaction which would take place if pure potassium were to be burnt in oxygen. It's nicely highlighted, underlined, and bolded there for you that we are looking for a word equation. So in words, I have potassium. Spelling, please. Potassium is a double S, and the IUM reacts with pure oxygen to make, and I write that as a symbol, the arrow, potassium oxide. So whenever something reacts, it forms a compound. When you have a metal bonding with a non-metal, the non-metal changes to an ide, and the metal just stays where it is. We don't need to use a di, tri, and tetra whenever there's a metal involved. Okay, question 6.7 says tripotassium phosphate reacts with BaF2 according to the following chemical reaction. BaF2 plus K3PO4, arrow Ba3, PO4 bracketed, 2 plus Kf. 671, write the IUPAC name for BaF2. IUPAC name, remember, is just the systematic or official name for a compound. So the name of BaF2, Ba is barium, and F is fluorine. When it's bonded, changes to fluoride. These are 2 words. Spelling is important. Fluoride, UO, and because there's a metal involved, I don't put a difluoride or anything in front of the fluorine. 672, write the IUPAC name for Kf. So Kf is just potassium, again with spelling, and fluorine changes to fluoride. 673, rewrite the equation BaF2 plus K3PO4, etc. as a balanced chemical equation. So balancing was the main topic of booklet 2, and there are many different ways that you can balance an equation. So I'm going to go ahead and use this table method where I write down the symbols of all the elements in the equation on the left-hand side. just going to rewrite the equation here. And as I do, I can pick up the symbols. So I've got barium that I need to count, fluorine, potassium, and phosphorus, and oxygen. And of course, on the right-hand side, there can be no new elements. Okay, it's called balancing because I'm trying to see if the left-hand side can be equal to the right-hand side. Starting with the bariums. So I have 1 over here, I have 3 over here. Count the fluorines, there's 2 over here. And on the right-hand side, there's only 1. Potassiums, there's 3 here. I'm counting the small numbers. Over here, there's only 1. Phosphorus, there's 1 on this side. And over here, there's 1 inside the bracket. But remember, it distributes and multiplies by the small number outside. So there's actually 2 phosphorus atoms. And then lastly, oxygen. I have 4 on the left and 4 times 2, which is 8. Now, a technique to balancing is to always start with an element that only appears once on each side. Now, that is true for all of them. So in this case, it doesn't really matter which element we start with our balancing. I'm going to start with the barium. So there's 1 on the left, 3 on the right. The side I'm short on is the side I'm going to manipulate. So balancing is all about changing the big numbers that go in front. Call them coefficients. We cannot be changing the small numbers. Those are fixed by the equation itself. So to balance 1 barium with 3 bariums, I can get 3 barium atoms by putting a big number 3 in front over there. That is now going to change my bariums to 3, just writing the silly sum about how I got to 3. 1 times 3 is 3. And by putting that 3 in front, it's immediately going to change my fluorine atoms, because as a coefficient, it distributes into the whole formula. I have 3 times 2, which is 6 fluorine atoms on the left. So because I've just balanced the barium, and that's changed the fluorine, fluorine is going to be the next element that I'm going to try and balance. So I have 6 fluorines on the left, only 1 on the right. To balance that, I can put a big number 6 in front that distributes and makes the fluorines 6. So I'm not crossing out because it was wrong, crossing it out because I've updated it. That 6 is in turn going to distribute and change my Ks. So my K will now also become 6. And that's going to be a hint as to the next element I balance. So 6 Ks on the right, 3 on the left. To get from 3 to 6, I'm always trying to multiply by a number. That number is going to be 2, because 2 times 3 gives me 6, which balances out the potassiums. But immediately it's going to change my phosphorus from 1 to 2, and my oxygens from 2 times 4, which becomes 8. Okay, so checking the next element. So phosphorus is already balanced, 2 and 2. Oxygen is already balanced, and this is now my balanced equation. You can put a big number 1 in front here. It's not compulsory, but I find it useful so that I know I have checked that this part of the equation is balanced. Okay, the next question. Nitrous oxide, N2O, is commonly known as laughing gas, or nitrous. It's a chemical compound made up of nitrogen and oxygen. When inhaled, N2O slows down the body's reaction time. This results in a calm, euphoric feeling. It means you're feeling very happy and relaxed. Nitrous oxide can be used to treat pain. It also functions as a mild sedative, puts you to sleep. It's sometimes a gas that dentists used to use before you undergo extensive, painful surgery. While the pizza was being burnt in the oven, a gaseous compound, which also contains only nitrogen and oxygen, NO2, is formed. So this paragraph is only telling me some interesting things about those chemicals, but importantly, it's showing me how nitrogen and oxygen can sometimes bond together as N2O, and sometimes they can bond together as NO2. Question 6.8. Michelangelo says that N2O and NO2 are exactly the same compound with the same properties because they have the same elements and number of atoms. Raphael says they are not the same. Who would you agree with? Explain your answer fully. So this type of question about criticizing a statement means you have to look very carefully at what they've said and identify the parts that are correct and the parts that are not correct. So before I write this down, so what Michelangelo is saying is that they are the same compound, same properties, because they have the same elements and number of atoms. So if I look at these two, N2O and NO2, are they the same compound? Well, no, because they have different small numbers, so they cannot be the same. Would they have the same properties? Well, from reading this paragraph, clearly not, because N2O is used as a sedative, while NO2 is produced when something is burnt, so they do not have the same properties. Do they have the same elements? Yes, they do. Do they have the same number of atoms? Well, in total, they both do have 3 atoms, but not the same number of each element. N2O has 2 nitrogen atoms, and NO2 only has 1. So that is criticizing the statement. Now, how we would write this down, notice it's only 2 marks, so we need to have at most, or at least, 2 points in our explanation. Agree with, meaning you need to give a name of one of the Ninja Turtles, and not your favorite, the one you believe is correct, which was Raphael, because Raphael simply said they are not the same compound. So we need to give justification as to why they are not the same compound. And of the many reasons I've mentioned, the most obvious one is because of the number of atoms. So how I would write this is that N2O has 2 nitrogen atoms. And if I just compare the nitrogen atoms, it's sufficient. But let me compare one idea, which is the number of atoms for both. So it has 2 nitrogen atoms and 1 oxygen atom, while NO2 that they make while burning the pizza has 1 nitrogen atom and 2 oxygen atoms. That's referring specifically to Michelangelo's statement about them having the same number of atoms. So in conclusion, why I'm agreeing with Raphael, they are not the same compound. And that's it. So question 6 was 20 marks. I spent roughly about 20 minutes on it. The multiple choice, I looked at 5 questions, each one 2 marks, which should take you about 10 minutes. So in describing these questions would take you longer than it would to answer the question, but always keep an eye on the time. Answer your best questions first. Make sure that you read the full question. Because very often you lose out marks by missing small things, like forgetting to mention the name of the person when the question asked, who do you agree with? All right, that's all from me. Hope that you have a good time studying through everything, reading through the notes, making your own extra notes, but most importantly, practicing the problems. All right, goodbye everyone, and happy studying.